Assalamualaikum dan salam sejahtera. So kita mulakan kuliah kita pada pagi ini dengan melihat beberapa contoh pengiraan yang melibatkan resistance ataupun friction dalam pipe. So previously in our lectures, I already introduced you two major equation. So one is losses in series pipe and another one is losses in parallel pipe. So for losses in series pipe, what you need to do is you need to sum all of the losses along the pipe. So in this chapter, we most probably use the equation of losses equal K Q square because I already discussed this matter. The changes of velocity is not change the friction condition anymore. So a few researchers tend to assume that all of that parameter, the F, the L, the V, and so on, is actually the constant. That's why we have a symbol of K here in calculating the losses. So I hope you could refer to our last meeting to derive or to prove this equation. So however, for the parallel pipe, okay, the calculation of the equation or the calculation to find the resistance is showing as this one. So you need to calculate, you need to first calculate the total 1 over square root K here, and then you need to solve these terms and get the value of K alone. Okay, I think, and then here I would like to show you a few examples. Okay, so this is example 1. So for example, we have this kind of pipe network. So the question is determine the flow rate at outlet and the percentage of valve opening. So for example, we have one inlet here, and then from point A here, it will be separate into two pipes. Okay, might be it has two housing system or whatever. So and then at point B it's merged together, and then it has a resistance here, and then at point C it's split into two direction. So one is go from C to D and E, and another one is go from C to F here. And then the total flow rate at inlet is Q, but at the outlet here, because it is separated into two two pipes, so one is half of them is one Q over 2, and this is also Q over 2. And the elevation here means that at inlet here, it's located 100 meters from the sea level. And however, at point E here, the pipe is only 40 meters from the datum, and at point F here, the elevation is 60 meters. And we assume that all pipes here have a 0.02 friction factor. And the details for each pipe is shown in this table. So for example, we have A1B means from point A here to A1 and B. So the total length is 30 meters. The diameter pipe is 0.1 meter. And then we could calculate the value of K. Okay, and to calculate this value of K, I think you already know. So this is the simplification of K, which is F L over D V square over 2G. So and then we could substitute the value of this one into this term. Okay, so I think the value of, okay, so we have this one. And then in this question, they give you the valve in this question. So if we see this one, they call this symbol or the resistance here is actually because of the existence of valve. So and then Okay, let's say what we could do is we could simplify the flow from A1B and A2B into a parallel pipe. As you know, this is a parallel pipe. So, and then we could combine these two pipes as this one. So it means that we try to simplify the flow from two parallel pipe like this into one single pipe like this one. So means that we now merging these two pipes. So because it is parallel, so we need to calculate its total K, total resistance. So we know that because it is parallel, so we use this equation, 1 over square root KAB, means the resistance from here to here is actually the summation of 1 over square root KAA1B plus 1 over square root KAA2B. So we substitute the value of K for each junction, and then we get these numbers. So please bear in mind that these numbers actually the value of 1 over square root KAB. So you need to calculate what is the value of KAB. So it is almost equal to 656. So and then we have a 3 point here. So from A is from the parallel pipe, it's straightened become to A and B here. And then we have another pipe from B to C here, and then to simplify our calculation, so why not we just merge these two sections? So because it is a series pipe, so we just add the value of K. So we adding the KAB and KBC. So we have 656 plus 1,304, and it is equal to 1,960. So now we could change this junction, this 3 points into this straight line. So it's only become A and C. So and then now we could use the idea of Bernoulli equation. So however we simplify the term, we do not calculate the F L over D V square over 2C. We just use the resistance. So we discussed in our first slide of this topic. So we could simplify that because we assume that the losses here is actually will be the difference of losses. So we write losses at A minus losses at C is equal to KAC times Q square. So we substitute the value of KAC here from what we get here, which is 1,960. So and then because at point C here, means after we simplify the parallel pipe, and the series pipe, we could draw our system pipe right now is from A to C, and then at point C here, so it's split into two junction. So one is go to F, and another one will go to D and E. Okay. So and then because it's split into two, so we need to calculate it differently. So because as you know, if you want to calculate by using the Bernoulli equation, as what we learned in fluid mechanics 1, so we need to calculate it into two calculation, because we only could compare the energy from A with energy at F, and also energy at A with the energy of E. It is not appropriate to compare the energy at E to the energy at F, because there are no flow between E and F. Please make some revision about how to use a Bernoulli equation. The rule of thumb is you must make sure that the Bernoulli equation is actually represent the streamline. So if there are no flow, or there are no streamline between E to F, or in the simple word, we could say that there are no flow, water not flowing from E to F or F to E. So water are flowing from A to F and A to E. That's why we only could compare Bernoulli equation from A, C, D, and E, and the other equation is A, C, and F. Okay, now because we want to calculate the value of Q here, and the first equation that we get previously from A to C cannot be solved because we don't know what is the elevation of C. If you see the question, the elevation only present for A, E, and F. Then okay, so now we are comparing the head loss between C and F. So for example, we have the equation of head loss C minus F is equal to KCF Q square. And we could calculate the equation for losses for KCF. So it is equal 4,950 Q square over 2. So because the flow rate here is Q over 2. And please make sure that you square this value Q over 2. All of these is actually square by the power of 2. Okay, kadang-kadang pelajar dia terkeliru, dia hanya menulis sebagai 1/2 Q kuasa 2. So awak kena alert bahawa kuasa 2 di sini adalah untuk kadar alih. Dan kadar alih pada point F di sini ialah 1/2 Q. Jadi awak kena kuasa 2 kan Q per 2 kuasa 2. And then you could calculate it is equal to 1,238 Q square. So actually the actual number is 1,237.5. So I round it up. So I just write is 1,238. So and then we have two equations. One is equation between point A and point C, and another equation is point C and point F. So then we could use this calculation. We could equalize with the value of Q square. So we have a Q square is equal of this one equal to this one. And then we substitute the value. It is given in the question that elevation at point A is 100 meters and elevation at point F is 60 meters. So, and then we could calculate the elevation at point C is equal to 75.5 meters. Then we substitute the value of elevation at point C here. So, and then we could get that the value of Q is equal to 0.111 H and 1118 meter cube per second. So and then we need to calculate the valve, means the value of N here. So because the question is given that that valve has equation of 4,000 over N square, I think. So and then we develop an equation between point C and point E. So we have the losses HC minus HE, and then it is equal to losses H means the height, and losses of CD plus DE, and the flow rate at point F there, it is equal 1/2 Q. So we write as Q/2 by the power of 2 here. So we substitute the elevation for point C, which is 75.5. Okay, I'm sorry. Okay, 75.5. So you need to substitute here. And then the elevation for at point E, as stated in the question, it is equal to 40 meters here. So and then you substitute all the values. So the K here, KCD is 2,475 and KDE is 4,000 over N by the power of 2. And then we already know the value of Q from our previous calculation. So we substitute in this term at this terms, and then we could get N is 0.4244. So it means that the valve need to be open 42.44% to achieve this situation. Okay, so if you see this one, okay, if you see this one from C to F, for example here. To develop this equation, you may use the idea of Bernoulli equation. So you have pressure, velocity, and height, and this is also pressure, velocity, and height, and losses. So and then we could assume that velocity is almost the same and the pressure is almost the same, and then the difference is only the elevation. So the H here is the elevation. Okay, so this is the example 2. So for example, we have one system like this. So we have a 2 input, and then it merge into one point at point B here, and then it become one single pipe here, and then it enters pump, and then from pump it comes out and split into 3 output. So and then all the parameters is shown in this table. So we have A1B, A2B, the length is 100 meters. So and then the diameter is 0.5, and another parameter is listed here. So the elevation of outlet D, E, and F is 100 meters above the elevation of inlet A1 and A2. So we imagine that A1 and A2 is on the same level, but the outlet of D, E, and F is 3 of these is actually 100 meters above the location of A1 and A2. So mean the D, E, F is assumed to be in one level, but that level is 100 meter high from the location of A1 and A2. So and then all outlet and inlet are open to atmosphere. If the mean velocity in the pipes A1B and A2B is 2 meters per second, so you have a 2 meters per second here, 2.5 meters per second here. So calculate the flow rate through the pump P. So the pressure difference across the pump and the power consumed. So we need to calculate 3 items, which is the flow rate through the pump, the pressure difference across the pump, means pressure difference before and after the pump, and the power consumed. And we need to take the pump efficiency as 76%. So I think you could imagine how to write Bernoulli equation if you have pump. You already know how to calculate Bernoulli. You know how to calculate the flow rate or the power input or output for the pump if efficiency of pump is given. So in this case, it is 76%. Okay, so because the pipe A1B and A2B is in parallel, so what we need to do is we need to calculate the total flow rate. So the total flow rate is we need to add both of that pipe's flow rate. So to calculate the flow rate, we can use the idea of A1V1 and A2V2. So we calculate all of these, so we could get it is around 0.982 meter cube per second. So you know, we have the velocity, and then we could calculate the cross-section area from the diameter given in the table. So we could calculate all of these parameters. So this is the total flow rate through the pump. So and then we need to calculate the pressure difference. So we calculating this one by using the total head loss. So the head loss before the pump is KQ square over 2. And then we could calculate the value of K by using the parameter in the table. So it gives you the value of F, and then you know the value of Q here. So you can calculate the KQ square here. So and then the K here is equal to FL over D over 2G. Okay, so you could calculate this one, and then again you could calculate the losses after the pump. So the losses after the pump, again you could calculate by using the equation of KQ square. So the K here can be calculated with the previous mentioned equation, which is F L over D over 2G A square. Okay. So and then the total here, because okay, the total here is we need to so the total Q is you just add all of them. Okay, why we add, so we add all of the value here. So and then we could get is 14.2865 times the flow rate here, which is 0.982 square, and then you will get 13.777 meters. Okay, please bear in mind these numbers is actually the energy, okay, the losses that between the inlet and the outlet. So why we need to add the losses here, because we assume that the parallel, it is some kind of parallel pipes in pump, so we need to add all the losses because we need to calculate the total losses for that system. So in fleet 1, okay, in fleet 1, might be we write as P over rho G plus V square over 2G plus Z. And then we have another one here, P2 over rho G plus V2 square over 2G and Z2. And then we plus a total losses here. So actually the total losses here is consists of losses that occur at inlet and also losses that occur at outlet. So in this situation, we need to calculate it separately because that is the easiest way for this situation. Okay, so and then we could calculate, we could derive our energy equation. So it is between inlet and outlet. So I think everybody knows to write this Bernoulli equation. So we have P over rho G, V square over 2G and Z. And then because we have a pump in our system, we need to add energy from pump in the inlet. So we add HP, and then we write the energy at outlet here at point number 2, which means at the outlet of the pump, and the total losses in that system. So we assume that the pressure is almost the same. So the velocity is also almost the same. Okay, because we are calculating about the inlet and the outlet of pump. So and then so the difference is only the Z here, and then we know that at point number 2. So at point number 2, the Z is 100 meters height. So and then we could have the 100 meter plus losses here will be equal to the head of pump. So and then it is equal to 113.777 meters. So and then to calculate the pressure difference across the pump, so we can use the equation of rho GH. So I think everybody knows about how to calculate the pressure. So we use rho GH, but in this situation, we need to calculate, we need to use the head of pump, and then we could get it is equal to 1,116.15 kilopascal. So please bear in mind that if the question asks you to calculate the pressure, so the unit must be in Pascal or kilopascal, or might be megapascal. So if the question asks you to calculate the pressure head, so the unit must be in meter. So the pressure head is in meter, the pressure difference is in Pascal. So and then okay, I forgot to explain it here. So how to calculate the head loss before and after the pump here. So you need to use the idea of parallel and series pipe. So you know the factor, you know the friction factor of this one and also this one and also these 3 parallel pipe. So means that for this one, okay, you need to merge these two parallel pipe and assume it as a one single pipe. So because it is parallel, so you need to calculate it resistance as 1 over square root k equal to 1 over square root k1 plus 1 over square root k2, okay, to get the total resistance, the total losses at the before the pump. And for the after the pump here, because we have three parallel pipes, so you need to calculate the same method with equation of 1 over square root k. So and then after you get all of that, inshallah, you will get this value. And then for the last question, we are going to calculate the power consumed, and you need to understand that power consumed means power need to be supplied to the pump, and it is equal to power in. And then I hope you could think like this. So power consumed or power in need to be a little bit higher compared to what you will use in the real operation, because the efficiency of the pump is 76%. So awak kena faham bahawa efficiency kecekapan pump ialah 76%. Jadi maksud kalau awak supply power adalah 100, oleh itu hanya 76 sahaja yang akan digunakan untuk menggerakkan pump. Kerana selebihnya 24% lagi akan digunakan untuk overcome friction. Okay, itu yang dimaksudkan dengan efficiency. Dan kita dah belajar berkenaan dengan efficiency di dalam fleet 2 secara mendalam, pengiraan dan sebagainya. Okay, jadi maksudnya kalau awak supply power adalah 76, so maknanya power yang digunakan oleh pump akan menjadi semakin berkurang. Okay, so di dalam keadaan ini kita kata, kita boleh mengira, so efficiency is actually power out divided by power in. And then power in or power consumed here, okay, can be calculated by using this equation, so which is the rho GQHP over mu, which is mu here is the symbol for the efficiency. So we substitute all the value here, we could get it is about 1.442 megawatt.